And let's talk about charging by contact. This is this is the stuff that you either, I guess you guys have, or I guess some students will do in lab, electrostatics lab. So charging by contact, this is when you just literally rub two things together and you create a charge. You sometimes do it unintentionally by scuffing your feet on the carpet and touching a doorknob, things like that. So let's take a look at how that works. So what you have is two objects. They are both neutral to start with. But you either intentionally or unintentionally rub them together and something happens. This is, by the way, the earliest kind of thing where people notice electricity, except possibly for the phenomenon of lightning, which you can't help but notice, but in your own hands. So here's what happens. When you rub them together a little bit, I don't know how to represent that, something like that, okay? What we have is that we suddenly find that they attract each other, and the name that was given to that is the electric force. And again, the bookkeeping for this was given plus or minus simply because it was found that once you rub these two objects together, they'll attract each other. If you rub another pair of objects together, they'll attract each other. But there's also a chance if you combine and cross pairs, the two might repel. So it was a system that was come up with by Ben Franklin, actually, who simply thought of plus and minus charge. So they thought that something was transferred from here to here. So this we call plus, this we call minus. And it was originally called that because plus, it was literally like plus, it was adding, it was like gaining something, and minus because it was losing something. So there's something that is traded between these two things. This is the Franklin convention right here. Now, which one do you choose to be plus and which one do you choose to be minus? Well, you just have to flip a coin and pick. There's no way, or especially back in that day, there was no way to tell what was actually being transferred to what. So it was purely just a 50-50 choice. So some reference material was thought of as being plus. Okay. So what you do here is you basically have a competition. It's like a round robin. It's like a tournament. What you do is you take a bunch of objects and you rub them together. So, you know, we can call like plus being like the winner, right? Because it gains something, and minus being the loser because it loses something. But just like in, you know, a basketball tournament, just because one team wins against another doesn't mean that it goes to the next round and has to win, right? It could win against one and lose against the other. So we basically have a ranking, right? We end up with a ranking if we have a bunch of materials. The thing at the top is the one that beat everybody else. It became plus when rubbed with everything else. There is a loser that lost every game at the bottom that lost every round, right? It always became minus. But then there's a ranking in between because sometimes it might win against one thing but lose against another, right? So we really have to rank this into a series. This is called the triboelectric series, or triboelectric series. It's a ranking of materials. So let me just give you kind of a results of the tournament. If you tried this with a bunch of things, glass will come out on top. It will win pretty much all the time, at least out of the materials I've listed. Hair, nylon, those are strong contenders. Silk, fur, aluminum, paper, cotton, rubber, PVC, and bringing in the rear, Teflon. Okay? So Teflon lost every game. Okay? So things that are up here tend to be plus, things here tend to be minus. Aluminum and paper tend to be around 500, as they say in sports, right? They tend to lose and win about the same number of games. They don't have any strong preference towards losing or gaining, right? They just kind of tend to, it really depends on who you match them up with. So for instance, I'll give you an example. If you had a game between hair and PVC, you would have that the hair would come out the winner, so to speak. Hair would come out plus, and PVC would come out minus. Okay? That doesn't mean that hair always comes out plus, because it means that hair mostly comes out plus. But if you, for instance, combine glass and hair, the glass would win, and the hair would have to become minus, right? So it's not like hair always becomes plus. It depends on who it's playing with, right? But just like you have a really strong team playing against a really weak team, it's going to be a blowout, right? So there's going to be a lot of charge transfer. And here, if you have two teams that are very closely matched, then it's going to be a squeaker, right? So much less charge transfer. In fact, the charge transfer can be so little that you might not even notice. And so in the lab, we try to give you widely different ranking materials. We try to give you stuff that is very high and very low on the list, and when you rub them together, you notice that they transfer charge, right? Hopefully. Unless it's a particularly soggy day, because then everything is wet, and that tends to, water's a pretty decent conductor, and all the charge tends to leak away, even into the air if it's too humid. Okay? So that's the triboelectric series. It's basically a ranking of who tends to become plus over who. All right? So let's talk about the mechanism of what's actually happening. Okay? We have the benefit of hindsight that Ben Franklin didn't have. And so we can figure out what's the mechanism behind this, and actually also figure out that he was just kind of wrong in what he was assuming. So you guys by now know, hopefully, in chemistry about valence electrons, right? That this idea that there's a kind of a set of electrons that a particular atom wants to have, right? So if it's a few shy of that, it wouldn't mind taking a few more to complete the set, right? If something is a full valence shell, but then a few extra electrons, it wouldn't mind dumping them, right? Because it's easier to dump the few extra you have than gain all the ones you need to fill the next set, right? Is this a familiar concept? Okay, so that's basically what this is coming from. Okay, now you can't just put the two next to each other, right? They're not just going to magically trade electrons just because they're sort of near each other. Because if there was no energy barrier whatsoever for either gaining or losing valence electrons, then they would just immediately just leak out, right? Could you imagine if you had an atom that had a full valence shell but just a few extra electrons and just dump them, just, oh, see you later. That thing would always be an ion, right? So to be neutral, it does have some mild desire to hold on to those extra few. But what we achieve when we rub them together is basically putting in a little extra energy into the system. So it takes those outer electrons, it kind of puts them up into a little bit of a higher energy, and when they fall down, they don't necessarily remember which object they came with. Okay? They tend to go to whichever side is more preferable. Okay? So it's kind of like the same thing at like when you go to your college graduation, right? At the end, you're supposed to throw up your hats. Okay? So in theory, if everyone throws up their hats, everyone gets a hat back. It may not be your hat, but everyone usually gets one hat back. But remember, that's because everyone has roughly the desire to take one hat home from graduation. Okay? But imagine if there was someone that was graduating in your class that really loved hats, okay? So when everyone threw their hats up, they just started gathering around like crazy, right? And gathering hats. They'd walk out of there with more hats than they came with, right? Or someone who's just totally over graduation just throws their hats up and like, oh, I'm out of here, right? Okay, they don't take a hat home, right? So that's what's happening when you rub these two things together, is that you're giving a chance for those outer electrons to go up for grabs, and then they fall more on the side of whichever thing wants them more, and away from the thing that wants them less. Okay? So when you're combining two things from the triboelectric series, what you're really doing is you're taking two things that have a different proclivity for electrons, and you're letting them kind of settle out. Okay? So even though they're both neutral to start with, they both have different kind of proclivities for wanting electrons. If you combine something from very high here and very low here, then they both agree, right? It's someone who doesn't want a hat and someone who really wants a hat, okay? If you put two things that are more closer together, maybe they both don't want a hat, right? You take the hat, no, you take the hat, no, you take the hat, right? So there's not going to be as much transfer, okay? So one of them has to win, one of them has a slightly different preference, right? It's like, no, I really insist you take the hat. Okay, I'm going to take the hat, okay? But the large charge transfer happens when you have two things from far apart on the series, okay? And here's the other thing. When we come up with this entire convention, we came up with more precise instrumentation, and here's what they actually discovered, is that this thing, which had all along been thought to be gaining something, which is why we call it plus, it actually it loses mass. And this thing, which we had been thinking of as losing something, actually gained mass, which basically tells us that the whole scheme ended up backwards. Okay? Totally understandable when Ben Franklin was just arbitrarily picking something to be their plus reference. But that tells us that it's actually being traded the other way. Okay? In fact, stuff is actually being traded this way. We call those things electrons. And that is how the electron got its minus sign in the first place. They're actually electrons going the other way, and it's too late to change it, so in fact, when the electron was discovered, it was promptly given a negative charge. That means that all the old stuff is still in place, and then once the electron is discovered, it has an annoying minus sign attached. So all of this mobility, all of this, what's being transferred is these valence electrons, or I should say electrons in and around the valence band. And it turns out that the convention was wrong, so when we say something is minus, it doesn't really lose anything. It actually gains something that has a minus charge. And when we say something is plus, it doesn't really gain anything at all. It actually loses minus charge. It loses electrons. This unfortunate historical fluke is still with us today. Okay, this idea that what's actually being transferred between things is the electron. Okay? So when something becomes positive, it actually loses electrons. We tend to call these electron donators. Things that are higher up on the series tend to get rid of electrons. So these are things that have a full valence shell plus a few extra they wouldn't mind taking out of there. And then things that are more toward the bottom of the series, these are things that tend to gain electrons. They are things which are more electron accepting, as we say. These are things which are missing a few electrons in their valence shell. They wouldn't mind a few more to plug those holes, right? In fact, if you know from chemistry something called electronegativity, this is a very similar concept. Triboelectric series is a little bit more informal. First of all, a lot of these things, they of course are not exactly chemical defined. Aluminum, of course, is an element, but there's many different types of hair, okay, or something like that, right? These are not all, like, you know, this is basically a more informal version of that, okay? It's just a ranking, okay, of different household materials. Okay, so that's the triboelectric effect. And one of the things I do want to point out is that since you are just transferring charge from one thing to another, the sum of the charge, of course, initially was 0 because neither of them had any charge. But if all you're doing is taking charge from one to the other, the total amount of charge still has to be 0 at the end, right? So if one becomes positively charged, the other one becomes negatively charged. It just means the same. You're still talking about the same particles on the two collectively. You've just shifted what lives on one to what lives on the other, right? So that's one of the things that in charging by contact, you will have something illegal if you find that your system suddenly has more charge on it than it used to as a whole. How did electrons or protons sneak in or out? There's a closed system, right? So the net charge overall should still be 0. It's just that one has now more electrons than the other. There's an imbalance. Okay? Are there any questions on that? Yeah.
So why is it that when I rub my hand on, let's say, a nylon pillow, and I walk across the room and I touch my dad on the shoulder, why is it that I can shock him?
Right. So
when he's a neutral object, or
right. So obviously, how you attain your charge is obviously because you're in a different. Your hand is in a different place in the triboelectric series as the pillow you're rubbing it on. As far as what causes a spark, that's something called dielectric breakdown, which we'll talk about around homework 4. So what is it that allows electricity to jump from your fingertip to something else, right? So we've gotten how you build up the charge, but we haven't gotten the second piece yet. We'll get there. Okay, so the next order of business we have is to put another category on materials. So we can, in the broad sense, take all materials and put them into two bins. These are called conductors and insulators. So conductors and insulators. Now, just for full disclosure, this is a distinction which is it's somewhat arbitrary. As many things in life, it's not so black and white. There's a gray area. In fact, we're going to turn out later on to loosen these two bins, and we're going to make it a continuum. Okay? So for the purposes of our discussion right now, these are going to be two different things, but there are going to be later, it's not going to be quite so sharp of a contrast. So, I'm going to tell you what is the difference between conductors and insulators, and you're going to have to take that without any kind of more complicated justification. And then, with that as being established, we'll find the consequences of what happens from these differences. So, a conductor is something where, let's take a chunk of conductor. It's a solid, so there'll be kind of positively charged nuclei. Now, of course, if you just had the nuclei, they would fly apart. Okay, they're all plus charged, of course. So that, but of course, they have around them electrons as well, right? And that's what causes chemical bonds, right? Is this idea that these two positively charged nuclei will consent to be around each other because they are sharing some electrons, right? Now, it turns out that they're in a conductor. Not all the electrons, but a very large number of electrons are shared. So they're not particularly beholden to any nucleus. They're just kind of free to roam, okay? So there's an electron, which is, I kind of just pepper them in like this. They're kind of just there, okay? So there's a large number of electrons which are not attached to any particular nucleus, any particular nuclei, I'll say. So if they have any reason to, they could literally travel from one end of the object all the way to the other. They're not constrained to be in place. Insulators, it's a different story. Here again are our nuclei. But the electrons all kind of have a owner. And so I'll kind of draw them bundled up like this. So here the electrons are bound to particular nuclei. I like to, the analogy that I like, the conductors are like the communists, and the insulators are like the capitalists, okay? Okay, so is the money shared by everybody, or is it owned by particular individuals? Only instead of money, here we're talking about electrons. Someone really didn't like this analogy at some point. I'm not endorsing any kind of particular system. It's just an analogy, okay? So as far as why this is, I'm not going to get into that because that's a whole different story. But if you can believe me that this is the case in various materials, the electrons are either bound or free to roam, we can work out a large number of consequences to this. And again, this is really not even a fair description to either say that the electrons are bound no matter how hard you try to rip them off, or the electrons are free. Really, there's a continuum here, and the continuum, just to give you an idea of what we'll get to, we'll do this on homework 3, I think, it's called resistivity. We use the letter rho for that. So that's a rating for how much the electrons are wanting to stay in place versus are able to be coaxed to go somewhere else, okay? And one of the most useful applications, I should say, is something called a semiconductor. A semiconductor kind of sits squarely between these two. A semiconductor is something where the electrons are owned, so the electrons are not mobile, until you say, hey, would you mind moving? And they say, oh, okay. And then it becomes a conductor. So a semiconductor, you can make it go from being one to being the other. This is useful for making computer chips, because in computer chips, making transistors, you may have heard of semiconductor even being mentioned around computers, is because the idea is you want to control electrical flow. So you want to use materials where it's like you can either choose or not choose to have electrons flowing. Okay? So we'll get to resistivity later. But for right now, what I want to do is I want to take these two kind of axioms or kind of starting points and see what the consequences of that are. So the approach I'm going to take here is that I'm going to start with conductors. And then I'll always kind of bring up insulators in the rear, because the general trend is that insulators kind of try to do the same thing, but they can't do it as well. So the insulators are kind of like, I'm sorry, I can't do that as well because the electrons aren't fully mobile. Okay? It'd be surprised if, since we're claiming at this point that they're completely bound, it might be surprising they can do anything, but it turns out they do have a little trick up their sleeve to where they can participate in the same phenomenon. Basically, while the electrons are not mobile, they're at least mobile in their neighborhood, right? They can at least choose where along their nuclei, they're stationed even if they can't go wandering off wherever, right? So they have a little bit of mobility, they just have a tight leash, right? So they can always do sort of what the conductor does, but not quite as well. Okay, so let's take a look first at a conductor. I'll draw it as a circular sphere of conductor because I don't know why. It's just a hunk of material. And I'm going to put it in the simplest electric field possible. This is not being caused by the material. In fact, the material is neutral. It's an externally supplied field, and just to make it as simple as possible, I'll make it uniform. I label it E external because this is due to something else which I haven't bothered to draw. We just talked about it earlier. It might be a infinite plane of charge or a parallel plate capacitor. It doesn't matter. That's not the point. I have the field. I want to see what does it do to this thing. Now, first you might say, well, nothing. It's neutral, right? It has no charge, and we learned that you have to have a charge in order to feel a force. Well, it's not quite. Because it's neutral, it simply means that, of course, it has an equal number of protons and electrons. But if the electrons are free to move, well, the electrons are going to pick up on this external field, and electrons, which way do they like to go? Do they like to go downstream or upstream?
Upstream.
Upstream, right? They feel a force against the field, so some electrons that are in that thing are going to move until they go clunk up on the inside edge. And, of course, this thing is neutral overall, so if there's more of a preponderance of electrons to the left, they had to leave behind some protons, right? So there's going to be some protons over here, so I'll draw those. And I'm going to be careful here and draw 6 of each because this thing is still neutral, right? It's just that now the pluses and minuses aren't all perfectly mixed. There's more minus on one side and more plus on the other. Okay? So now what has occurred, this thing is still neutral, but it's what we call charge polarized. So there is a separation of charge. It's not all sifted in perfectly evenly. There is more of one type of charge on one side and more of the other on the other side. Right? It's like when the House of Representatives is polarized, right? That means there's a lot of really extreme left wing and really right wing people, right? So they've separated, okay? There's not a lot of middle ground, okay? So same usage of the word polarized. So, what does this mean? Well, first of all, these minus charges were pulled to the left. They were pulled upstream to the external field. And now that they've gone clunk on the inner surface, well, they, of course, will continue to exert a leftward force on the inner edge. The only way they can continue to move and relieve that force, so to speak, is if the object were moved, right? So now that they've gone as far as they can without jumping off the object, they continue to exert a leftward force. They continue to desire to go up there, right? And these positive charges feel a force downstream to the field. So looking at that, what would you expect the net force to be on this object? 0. The net force is 0 on a neutral object in a uniform E external. Because everything's the same, right? It's the same amount of minus charge on one side and plus charge on the other, right? So the charges amount's the same. Remember, it's neutral, so it has to be. And then both the plus and the minus charge are in the same strength of field, right? The whole field is uniform, so everything's the same strength. So there's no tiebreaker here. The net force is 0. But that is because the field happened to be uniform, which is more unusual than not, okay? So let's take a look at what would happen if it wasn't uniform. Let's say the external field looked like this. It got weaker as it went to the right. So it would have a similar charge polarization. I guess I'll draw 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. of each. The same thing holds. There's a leftward force and a rightward force, but which force is stronger?
Left.
The one that's in the stronger field. So this is a stronger field. Bigger force, smaller force, right? Once the charge is polarized, we now have that even though there's equal and opposite charges on the two sides, one is on a stronger field and one's in a weaker field. So in this case, the net force is this way. So the net force is not zero in a non-uniform field. In fact, as you can see here, it's into the region of stronger field. It's towards stronger field. Now, what could be causing that field? Well, this is actually more common, right, for a non-uniform field. Maybe what's causing it is the charge. So the reason why this field is stronger over there is because you're closer to the charge, right? And so what we find is that a neutral object is attracted to a charged object, okay? So towards a stronger field is actually towards the charged object. So this is the part that no one really ever tells you, the corollary, right? You know like charges repel and opposites attract. But did you know that charged objects can attract uncharged ones? The only thing that has to happen is for your object to have a finite size. Because finite size means that when you separate the two charge polarization, one half of it could be in a stronger field than the other half. There's a common name for this. It's called static cling, right? They have commercials to say, hey, buy our dryer sheets to prevent static cling. What is going on? Well, you have a bunch of clothes in the dryer, right? It's very low moisture in there. And you have so that you don't have any humidity to let the charge dissipate. And you have a bunch of clothes made out of different things, different fabrics, and they're all in different parts of the triboelectric series, so they get charged, right? Sometimes if you forget to put in a dryer sheet, right, you have to pull them apart. That's because they're attracted. One's become plus and one's minus. But then, once you have one of those pieces of clothes, it sticks to everything. It sticks to the wall. It sticks to you, other neutral objects. That's why. Because once it's charged, it can attract uncharged things. Okay? So that's, remember, static cling. You guys either have or will try this with the packing peanuts, right? So you guys charge something and then you attract the little bits of packing peanut which are neutral, right? That's how it works. You charge polarized it. Now, you might say, packing peanut, is that a conductor? Well, it turns out that this phenomenon does not depend on it being a conductor. So while I've started with that, it's not necessary. Okay, so I'll start next time doing some comparing and contrasting of how much conductors and insulators participate in this, but they do both exhibit this behavior. So I'll do that next time.